Alright guys, this is Algebra 2 3.1.3 Day 2, and we're going to be finishing off what we started last time. So we're going to start off by looking back at the very last problem from yesterday. So problem F that was purposely a little bit more challenging. It's very doable with our current methods, but it takes a long time, and even if you few little tricks to it, it's kind of nasty. So they're trying to get you to see, hey, is there a better way for me to actually approach problem F here? So they introduced what's called the idea of a U substitution. So I'm going to jump over to my document camera and kind of show you kind of how this works. I'm not going to run through problem 39 exactly as they kind of walk through it. I'll kind of go through it in my own way here. So our system is, get some room here. There we go. Is the square root of x squared minus 15x over 2y equals 5. Then our other equation is this 3 times the square root of x squared minus 15x minus 3y equals 27. So the commonality here, let me try to zoom in better. There we go. So the commonality here is that square root part, right? And this is the kind of key to the entire thing. The fact that I have the same square root over here as I do over here is what allows me to kind of do this. So I'm going to try and say, well, since that's the problem, and it's really big and ugly and nasty, let's try and replace that. So I'm going to do a U substitution. It's called that because we just use the variable U. But whenever I introduce my own variable, I have to define what that variable is. So I'm going to define U by saying let U equal, and then I want it to equal that part there, which is the square root of x squared minus 15x. Now you can let U equal whatever you want, but in general, the rule is you want to make it the largest thing that is common between both of your equations, or see multiple times in your one equation, depending on the context which you're trying to do here. So if I do that, what do I get? Well, I can replace this with just U, and I get U over 2y equals 5. And over here I get 3u minus 3y equals 27. Well, already, that is a drastically easier problem for me to solve out. And that's what I want to do. So go ahead, pause the video, solve out this system, and solve for what u is and for what y is, and then unpause. Okay, so if we solve this, we're going to move that. We'll move this over, so we get u is equal to 10y. Over here, we'll divide by 3 and get u minus y equals 9. Subtract over the y, I get u equals 9 plus y. So then I can set these both equal to each other because they're both equal to u. So I get 10y equals 9 plus y. So subtract over this y, I get 9y equals 9. So y equals 1. So there's my first variable. Now to find u, I can take this, I can plug it into either the y here or the y here. Either way, 9 plus 1 or 10 times 1 both give you 10. So I get u equals 10. So awesome, I found y and u. Easy. But again, I'm not done because I'm not trying to find y and u, I'm trying to find y and x. So to find x, I just got to take this, u, and plug it back in here where I defined u. So I'm going to say, well, then 10 is equal to that big radical. So 10 equals the square root of x squared minus 15x. Now go ahead, pause the video again, solve this for x, see what you can do. Alright, so first thing that we want to do is square both sides. I get 100 equals x squared minus 15x. I have a quadratic because I have an x squared and an x term. So I move this 100 over because I have to get it equal to 0 whenever I have a quadratic. And now I can try and factor it, and this one does factor it easy for us. What multiplies to be negative 100 adds to be negative 15 is going to be negative 20 and positive 5. So I'm factored. Zero product property will tell me that x has to be either positive 20 or negative 5. So my final answer is we always want to write those in ordered pairs. So I would have the point 21 and the point negative 5, 1. Right. So those are my solutions. So that's the whole point of a U substitution, right? It takes the ugly problem makes it pretty, right? Then we do the hard work, which is that system while it's pretty. And then once we've done that, then we can go back to the ugly part and deal with the ugly part by itself. Now the thing about U subs is you never have to do a U substitution, but when we do them, they just make our job a lot easier. It's a way for us to take a big ugly thing, break it up into the smaller chunks, and do those chunks individually, which will make our problems a whole lot easier for us. All right, so this next one, we're just trying to say what the U substitution would be. We're not trying to actually do the U substitution here. So go ahead, pause, and on number 40, tell me what would you make U for A, what would you make U for B, and what would you make U for C in order to make it a simpler problem. And then come back here. All right. So on A, we're definitely going to want to make U this whole thing here. So U is m squared plus 5m minus 24. So then we get U squared minus U equals 6. And that's really easy for us to solve out. So that one's going to help out a ton, right? On B, I would probably make U y to the 7th power. So then I have 2x plus U and 3x minus 2u on this side. And then it's going to be a lot easier for me to solve than trying to work with that 7th power while it's still in that original state. Now on C, the biggest thing that is common here is x to the second, but we actually don't want to do that. Because if we do that, then we're going to have both u's and x's still in our equation. So there's not a good u substitution here. And this is just to kind of show you don't always do a u substitution because it's not always going to be beneficial to us, right? Again, the general rule is you want to replace the entirety of a variable. So if you're going to replace something with x's, you want to replace every single x. If you're going to replace something with y's, replace every single y. And you want to have it be decently large and messy of a thing to make your job easier. Because if you're just doing x to the second, well, yeah, that can help at times, but you got to think, well, does this actually make my problem easier to solve? Which sometimes it will, but other times it's not really going to do a whole lot for you. All right, so moving on to just down to 41. So go ahead and on A and B solve those both for y. So you get y by itself, so it's y is equal to everything else. And then come back here. All right, so my hope is that we did fine with doing that, but the challenge is going to be on number 42. So on B, we're trying to get x by itself. So what I want you to do is go ahead and pause again, try and get x by itself here. There is a trick to it, which you might have a hard time with, but give it a shot. Once you get kind of stuck, then go ahead and unpause and come back here. All right, so on this one, we have xy plus 3x equals 2. So the trick here is I want to pull out a greatest common factor. My greatest common factor of these two values is x. So when I do that, I have x, and then I have y plus 3 left over. Now what I've done is I only have a single x left in my problem, because what made the original hard was there was an x here and an x here, and you couldn't really separate those two or combine them to get one. So we have to actually pull out the x. Now I have this bit, which I can just divide off. So divide both sides by y plus 3. And I get x equals 2 over y plus 3. Right? So that's a fairly simple trick, but you're going to want to use it fairly often, especially as we go forward and deal with more and more complex problems. You've always been able to do it, but you just really haven't done greatest common factoring in this kind of context. So we're just trying to kind of show you that, because you're going to want to be able to do that kind of moving forward here. All right, so let's head on to the last little bit here. All right, so on 43, we're trying to say, hey, are any of these three equations equivalent, right? So we basically want to get them into their simplest form and then say, hey, are they equivalent? So go ahead and pause, try that out, and then come back here. All right, so we have our first one being 2x equals 2y minus 6. So I can divide everything by 2 and get x equals y minus 3. Okay, that's as simple as that one's going to get. My next one is xy plus 2x equals y plus 2 times y plus 3. So Again, your instinct might be, let's multiply this out, which will work if you do that, and then combine like terms and such. But it's going to be drastically easier if we do the same thing as we just did on that last problem here, right? We're going to factor out an x, and I get x times y plus 2 equals y plus 2, y plus 3. Well, now, to get this x by itself, I want to divide by y plus 2. When I do that, it cancels out on both sides. Goes away there, goes away there. I'm just left with x equals y plus 3. Awesome. Well, that's not equivalent because one's a minus 3, one's a plus 3, but they're pretty darn close. And then my last one I have is negative x equals negative y minus 3. Well, I multiply everything by a negative 1 or divide everything by a negative 1. Does the same thing. X equals y plus 3. So then these two are going to be equivalent for me. And there we go. All right. So if we hop over and take a look at number 44. So their argument is that, well, if I solve these two problems, right, x minus 3 times x minus 5 and 2 times x minus 3 times x minus 5, if I set them equal to 0 and solve, I get the same answers, right? I would get positive 3 and positive 5 for both, right? So does that mean that they're equivalent statements? Well, no, is the short answer here, right? So effectively what this is this is the same function on this side as it was over here, but we put a 2 in front of it. So what this graph actually looks like is, if we graph it, this is a parabola that crosses at 3 and 5, so maybe it looks something like that, right? Crosses at 3 and at 5. Awesome. But multiplying that 2 out in front of it does that vertical stretch, right? So what it'll do is it'll cause every value to be stretched vertically, but I still go through those same spots on my x-axis. So I get that purple graph, in a sense, right? So those are two different graphs. They just happen to have the same x-intercepts. So the big point here is, even though we get the same solutions, it doesn't mean we have equivalent statements, right? They have to be exactly the same in every way once you simplify them down. And that little 2 there, while it doesn't change the final answer when you try and solve it, it does change the actual graph in the E equation for every other value other than those two x-intercepts. So that's the last thing that we wanted to kind of cover there. All right, let me pop over this. Okay, so note-wise, go ahead and read through those. Those are all terms you should have seen in the past. If there's things there you don't quite know or you think you need in your notes, then go ahead and take those down. Other than that, here's our homework for day 2. We're doing 51 through 56, and I will talk to you guys next time.